Hi everyone, this is Didong. I'm a postdoc at Princeton and UCLA. Today I will talk about manifold approximation with spherelets. And this is the joint work with Minerva Mukhopadhyay from Indian Institute of Technology and David Johnson from Duke. So first I will talk about the background and motivation of this project. Then I will propose a new dictionary called the Spherelets for manifold approximation. And the key step is the so-called SPCA or spherical PCA. At the end, I will talk about some theory and examples of SPCA. We all know that it's very typical in modern science to collect high-dimensional complicated data. Unlike in many applications, we often have limited sample size, and we don't just want a black box for prediction, but instead we want to learn and interpret the load dimensional structure and relationship in the data. So that means we need some sort of dimensional reduction before further analyzing the data. For simplicity, we assume we have IID samples xi, where this xi is living in a p-dimensional Euclidean space. This p can be huge. Then the dimension reduction method can be based on the model xi is equal to f of eta I plus epsilon I, where this eta I is called the latent factor, and we assume the dimension of the latent factor is small d, much smaller than the ambient space dimension p. F is some unknown function we want to learn, and if epsilon I is the zero mean measurement error. We always assume this epsilon I follows a Gaussian distribution with zero mean. So suppose F is linear, then we can use some well-established method like factor analysis or PCA. And what if F is essentially nonlinear? Then we have two approaches basically. Approach one is to use a locally linear approximation. That is, we cluster the data first and then apply a linear method like PCA in each local neighborhood. The intuition behind approach one is that the remaining manifold can be approximated by its tangent space locally. Approach two relies on some black box method. Consider this nonlinear factor model. We assume eta I follows a standard Gaussian distribution, and f is some unknown function we want to learn. So approach two includes Gaussian process latent variable models and variation autoencoders. These are both black boxes and lacking identifiability and interpretability. Our goal in this talk is to develop simpler approaches, including nonlinear alternatives to PCA. So to develop method and theories, we need some sort of assumption on the data. So here we assume the data xi are concentrated around a manifold M. So this figure shows a two example of the spherel. It's a two-dimensional surface embedded in three-dimensional Euclidean space. So manifold learning algorithms seek to exploit the manifold structure through some mapping from the observation xi to the latent factor eta I living in a low-dimensional space, while preserving certain structure. So for example, if the pairwise distance is preserved, then we have the iso map. Similarly, with the Hessian local linear embedding, Laplacian eigenmap, diffusion map, Tisney, etc. And there's a misnomer that the manifold approximate M hat is not typically produced by this algorithm. Instead, the outputs of these algorithms are just the latent factors eta I. We still don't know what does this manifold M look like in the original space. So algorithms that actually learn the manifold usually require a dictionary because global method is not good enough. We need some local method. And each local basis is an element in the dictionary. So dictionary are made up simple pieces used in approximating manifold M. Almost always the local patches are linear. Using simple linear pieces are conceptually nice and appealing computationally. Also, it matches the intuition. That is, the manifold can be approximated by its tangent space locally. But the problem is we need too many pieces to approximate a manifold M with large curvature. For example, in this figure, the manifold itself is just a simple circle, and we can use 17 tangent lines to approximate manifold M. But you can imagine, because each tangent line is flat with zero curvature, but if the manifold has large non-zero curvature, then the approximation performance will get worse. So the natural extension from first order approximation is to the second order approximation, which is written by this quadratic function x transpose hx plus f transpose x plus b is equal to 0, where this h is a p by p symmetric matrix, f is a p by 1 vector, and b is a scalar. We can even generalize it to a polynomial with degree k. This is called a generalized PCA. We can even consider some non-parametric method like the principal curves. The problem is the number of unknown parameters will be much greater than the order of p square. If we consider the second order approximation, this is p square. If it's a degree k polynomial, then it will be p to the k. So we don't want to treat one problem for the other because this p is sometimes huge. But we want something in between first order and second order approximation. So we call this 1.5 order approximation. So consider the simplest quadratic form. So the orders of p square here comes from the matrix H. So we consider simplest quadratic form, that is, we set H to be identity, then the number of unknown parameters will be of order p. And this is from the algebraic view. So what about the geometric perspective? So H equal to identity is equivalent to say the surface itself is a circle or a sphere, or is a constant curvature space. And we can rewrite the equation of the circle as the distance between x and the center C is equal to radius r, or we can write it in a quadratic form where the matrix here is exactly identity. Okay, so this figure shows the intuition of the oscillating circle. So the black one is a curve denoted by C, and P is a point on the curve. And this blue circle is the oscillating circle, which is the unique circle that is tangent to the curve at point P with curvature equals to the curvature of the curve. And this radius r is called the curvature radius. And you can tell from the figure that this oscillating circle approximates this curve C much better than the tangent line. Okay. So we propose to use PCAs of spheres or spherelets as a new dictionary. Often there are many fewer spheres that have hyperplanes to obtain the same error. And each sphere has few parameters. Basically, the order is the same as the linear method. And these are very simple geometric objects that are easy to fit. So then the question is how to find the best sphere based on some observations. So for PCA, in order to find the best hyperplane, you just need to do the eigendecomposition of the coordinate matrix, and the best hyperplane is just spanned by the top eigenvectors of the coordinate matrix. So what about the sphere? So we develop a method called the spherical PCA as the analog of PCA. It can be used to find the best or the optimal sphere from the data. So here's the definition of the solution. So let X be the data matrix, where this N is the sample size, P is the dimension of the ambient space. So each row represents each observation. And D is the intrinsic dimension, which is much smaller than the ambient dimension, P. And optimal sphere for the data X is given by this equation, where this V hat is a low-dimensional hyperplane, C hat is the center of the sphere, and R hat is the radius of the sphere. So the D-dimensional SPCA is the projection of the original data X to the best D-dimensional sphere, given by this closed form equation, where Xi is the observation, V hat, C hat, R hat are the estimator from SPC, and Zi hat is the projection or the principal component of the data. And you can tell that everything here is in analytic form, so we don't need any gradient descent or some other numerical method. And this SPCA can be trivially used in place of PCA in board settings. We'll see this later on in this talk. So then let's look at some theoretical result regarding SPCA. So first we assume that xi comes from a point on the sphere with some measurement error epsilon I. That is, yi is from some sphere parameterized by v0, z0, r0. And this epsilon I is the Gaussian noise with variance sigma square. And then we have some IID samples, x1 up to xn, and we run this SPCA. We get this vn hat, cn hat, and rn hat. So we'd like to know what's the difference between these parameters, between this estimated parameter and the true parameter, and what's the difference between the true sphere and the estimated sphere by SPCA. So under mild conditions with high probability, we can show that the error of the parameter can be bounded by these quantities. And you can see that the order here is basically 1/2, which is not surprising. And similarly, the Hausdorff distance denoted by dh between the true sphere and the sphere estimated by SPCA is bounded by the same order error. So this theorem basically says that if your data are from some sphere, then we can recover this sphere with high probability as long as we have enough samples. Then what about the manifold case? We want to weaken this condition, weaken this assumption here. That is, we have some xi from some noisy observation on a manifold M. So here fyi is from a manifold M, which is assumed to be compact and third differentiable. Epsilon I is again the Gaussian noise. We want to recover this manifold M. Then given some smart partitioning algorithm, that is, we cut the space into a lot of local pieces, and for each local piece, we run SPCA to get the optimal sphere, and then we let M hat to be the union of such local spheres, and that's the approximation of the manifold M. We show that how the uniform error converges to 0. So under mild conditions with high probability, we can show that the sup of the distance between a point x on the true manifold and the estimated manifold is bounded by this quantity. And note that this error is the uniform error or the sup error. It doesn't depend on the point x on the manifold. Here the rate is 2 over d plus 4. And I want to remind you that the optimal rate here is 2 over d plus 2. So our rate is almost optimal. Okay. And then remember that we claim that the number of pieces used to approximate the manifold of by spheres is smaller than the number of pieces of hyperplanes. So we'd like to show it as well. So we want to bound the number of pieces needed to obtain the approximation error epsilon. Let an h epsilon m be the minimum number of hyperplanes. Let an h epsilon m to be the minimum number of spheres. So this m is the manifold, epsilon is the error, and h means hyperplane, s means sphere. So we can show that the minimum number of hyperplanes is bounded by epsilon to negative d over 2, while the minimal number of spheres is bounded by a linear combination of two terms. The first term has rate negative d over 2, the second one is negative d over 3. And we can consider two extreme cases. When alpha epsilon is 0, and then these two upper bounds are the same. So that's the worst case for spherelets. Okay, the other extreme case is when alpha epsilon is 1, then we decrease the order from negative d over 2 to negative d over 3. So that means the spherelets can decrease the impact of the curse of dimensionality from negative d over 2 to negative d over 3. And I will not talk about the detail of the of this alpha epsilon because it's very complicated. But the as far as we tested in the on the real data sets, this alpha epsilon is sometimes large. At least it's far from 0. So that means we have a big gain in terms of the number of pieces. Here's a figure shows how spherelets work. So the true manifold here is called the Euler spiral. It's a curve where the curvature grows linearly with the arc length. And you can approximate it by a bunch of tangent lines or local PCA, and each color represents each local piece. And you can also approximate it by a bunch of spheres or local SPCA, and you can tell there are fewer number of circles than number of tangent lines here, and also look at the intersections between two regions, and this local SPCA is smoother than local PCA approximation. Okay, and so the main theorem suggests that we should see big gains in practical performance, and we initially develop simple local SPCA algorithm and compare to local PCA and this state-of-the-art algorithm called the geometric multi-resolution analysis. So recall these two examples, the space row, and the x coordinate is the log of number of partitions, and the y coordinate is the log of MSE, or the mean square error. So the lower the better. You can tell that the Spherelets is the best among this algorithm, while the red one is the local PCA. The middle two are from the two versions of GMRA. So the results show that Spherelets produces dramatically lower MSE curves than locally linear method. And we also tested on multiple real data sets, and we observed similar pattern. So this matches the theory. So the take-home message for today is that we can use spheres instead of hyperplanes for local approximation for a manifold. And we can replace PCA by SPCA. And there are many applications like manifold learning, denoising, data visualization, density estimation, classification, geodesic distance estimation, clustering, conditional density estimation, and regression. So for each of these applications, once you have an algorithm that involves PCA, you can replace the PCA part by the SPCA, replace the PCA projection by the spherical projection. You will get a spherical version of that algorithm. There are also some future work. For example, we want to further generalize the spheres to ellipsoid or quadratic surface. But the problem is if we consider ellipsoid or quadratic surface, we will lose that analytic solution of SPCA, as well as those nice series. And also we want to scale up to large ambient space dimension P and large sample size N, like we have want a sparse portion of SPCA or sparse SPCA. We also want to address non-Euclidean data like categorical data or functional data. So that's all of my talk. Thanks for listening.